Hello everybody, it's Mr. ARocena, and on today's video we're going to be talking about magnetic forces on charges. Alright, so in the last video we talked about magnetic force, and today we're going to expand on that a little bit. Alright, so previously we found that moving charges can create magnetic fields. So magnetic fields are the result of moving electrons. So if I have a current in a conductor, then the current in the conductor will create a magnetic field. And if I place that current that's creating a magnetic field inside another magnetic field, it will feel a force being exerted on it. So if I take this, for example, so this is a current carrying wire. Current carrying wire. The X means the current's going into the page, and I place that in another magnetic field. What will happen is that because this wire is creating a magnetic field that will, according to the right-hand rule, the magnetic field of the wire will operate in this direction, so it's going to spin in this direction. This magnetic field around the wire will be affected by the magnetic field of the magnets, and the wire will get pushed around. Now, which direction will this wire get pushed in? Alright, to determine which way this wire is going to get pushed, we're going to revisit the right-hand rule. Alright, so the right-hand rule revisited. Last lesson we talked about the right-hand rule. Here's a diagram this time to help us determine kind of how to determine where the force is going to be exerted. Alright, so the change we make here, I guess, is which part of your hand refers to what quantity that we're dealing with. So the thumb will still point in the direction of the conventional current, okay, the direction of positive charge. So if this was a single charge, then this would basically be the direction of motion. For a charge in a wire, it'll be the direction of the current, okay. The fingers will point in the direction of the magnetic field. So this is the outside magnetic field. Direction of magnetic field. And I'll make a note, this is the outside magnetic field. Not the magnetic field caused by the wire or caused by the charge, but the magnetic field that the charge is in. And then the palm will determine the direction of your magnetic force. Okay. So thumb is direction of current. Fingers, direction of outside magnetic field, and the palm will tell you where the force is going. We can use the exact same right-hand rule for moving point charges. So moving point charges, we can use the same rule. And if we're dealing with negative charges, we just simply use the left hand instead, with the same conventions, where the thumb is the direction of the current or the electrons, or charge, direction of charge, movement. Fingers are still in the direction of magnetic field, and palm is direction of magnetic force. So with this in mind, if I go back to this diagram here, and I were to follow the directions, I would point my thumb into the page. So the thumb would go into the page, the fingers would go in the direction of this magnetic field, so your fingers would point in this direction, and their palm will tell you which way the magnetic force will go. So if I do this, my thumb pointing into the page, my fingers pointing in the direction of the magnetic field, then the force, your palm, should be pointing up this way. This would be the direction of the magnetic force. So this wire would then be pushed in the upward direction, which kind of makes sense, because if I consider that the north end of, consider the motion of a north pole, and it's going to go this way, it's going to collide with the north lines here and cause this to get pushed up. And then similarly, if I have a north end traveling in this direction towards the south end, this part of the magnetic field is going to get pushed up this way. So that's sort of that combination of both sides being pushed up will cause the magnetic force to basically cause this wire to go up. So if I place this wire in this magnetic field, I can expect the wire to be moved in an upward direction. Alright, now to calculate the actual force is dependent on the amount of current flowing through the wire. And also, oddly enough, depends on the orientation of the wire. So the magnetic force can be calculated as follows, where we have magnetic fields. This is my outside magnetic field. So again, not the magnetic field caused by the wire. I will be the current in the wire. Current in L. L, this one here, that's the length of the wire in the magnetic field. And then theta is the angle that the magnetic field is relative to the wire. For almost all cases, theta will be equal to 90 degrees. We tend to keep, at this level, we tend to keep our angles perpendicular. So if theta is equal to 90, then that means that sine theta is equal to 1. So this equation basically reduces to BIL. And then the direction can be determined using right-hand rule. Direction determined by right-hand rule. Okay. Alright, so let's see if we can put everything into practice. The right-hand rule along with this equation. So let's say I have a wire of this length, 32 centimeters. We place in a magnetic field of 0.21 Tesla, and the current in the wire is 0.6 amps. What is the force acting on the wire? So we're going to assume that this magnetic field is perpendicular. So the magnetic force can be calculated using B times I times L. Our magnetic field is 0.21 Tesla. We have a current of 0.6 amps flowing through it, and we have a length of 32 centimeters, which will convert to meters as follows. Putting all this into our calculator, putting this in our calculator, we get the following: 0.04032 newtons, or approximately 0.04 newtons of force. Alright. The direction, this will depend on the orientation of the wire in the magnetic field, and since we don't have a diagram, we can't really say what the direction is. Alright. Next example, here we're not given any numbers, we're just asked to determine what the direction of the force is. So this is a wire. The dot represents the current flowing out. Current is going out of the page. So we can point our thumb going out of the page towards us. The magnetic field goes north to south like that, so our fingers would point going from north to south, so I guess right to left. And the palm will tell us which way the magnetic field or magnetic force is going. Magnetic force in this case, my palm is pointing down, so my magnetic force is going in that direction. So I would expect this wire to be pushed down. Alright, so that's how we can sort of deal with magnetic force on a current inside a wire. We can use this, like I said, we can use the right-hand rule for moving point charges as well, but there's some other considerations we have to take into account for a moving point charge. Now, being a charged particle and moving, it does create its own magnetic field. Now, if this charged particle moves into another magnetic field, because there are two opposing magnetic fields, or I guess two attractive magnetic fields, then the charged particle will feel a force. Now, the calculation for the magnetic force on the moving point charge is slightly different because rather than having a current, we just have a single charge that is moving. So the equation is almost the same. We just have, rather than having I, we have a charge. That's Q. Charge is Q. And then speed of charge. Speed of charge. And theta again is the orientation of the magnetic field relative in relation to the motion of the particle, but we tend to always stick with perpendicular motion and perpendicular magnetic fields, so this ends up usually simplifying to Q times V times B. More complicated problems, you'll have the magnetic field oriented at a non-90 degrees to the motion of the particle, in which case theta will be some non-90 degree value, and then you'll have to take into account the full motion. But for our purposes, we'll just stick with 90-degree angles, and then we can simplify the equation to that. All right. So here we'll throw a proton traveling with a speed of 3.4 times 10 to the 6 meters per second, so not quite the speed of light, to a perpendicular magnetic field of 6.2 Tesla. And we're asked, what is the magnitude and direction of the force on this proton? Alright, so first direction. Direction is easy. We'll just use our right-hand rule. Again, thumb points in the direction of the current, so thumb will point this way. This is not direction of current, direction of charge movement, so it's pointing that way. Fingers will point in the direction of the magnetic field. So in this case, my magnetic field is pointing up, so my fingers will point up. And in this orientation, the palm of my right hand is pointing towards me. So the magnetic force will end up coming out of the page. So force magnetic goes out of the page. So there's my direction. The magnetic force is directed out of the page. So you can imagine that this proton, as it's moving through this magnetic field, is going to be pushed towards us. Now to calculate the magnitude of the force, we can use our equation, Q times V times B, and we'll just fill in some values. The proton is an elementary particle, so it'll have elementary charge. 1.6 times 10 to the negative 19 coulombs, traveling at 3.4 times 10 to the 6 meters per second, and our magnetic field is 6.2 Tesla. 6.2 Tesla, by the way, is a ridiculously large amount of magnetic field. The Earth's magnetic field is nowhere near that size. Put all that into our calculator, we get the following: 3.37 times 10 to the negative 12 newtons. To two significant figures, 3.4 times 10 to the negative 12 newtons. So this proton feels a relatively small amount of force, but keep in mind the proton is not that massive, so this force will actually cause it to change direction quite drastically. Another example. So here, no numbers, but we're asked what direction does the electron beam bend when it passes through a magnetic field like below. So here we have an electron this time, and the electron is slightly different than the proton in that it doesn't have a positive charge. In this case, the electron has a negative charge. So having a negative charge means that we're going to use our left hand instead of our right hand to determine the direction of things. Okay, so like before, thumb will point in the direction, so thumb will point this way. Okay, but remember we're using our left hand, so left hand thumb points that way. The magnetic field is going out towards us, or out towards us, yeah, out towards us. So our finger should be pointing towards us, our thumb is pointing from left to right, which means that the magnetic force, my palm, tells me my magnetic force is going in this direction. Okay, there we go. Now here's something that's really interesting. This magnetic field, because it's much larger, or the picture is a little clearer, it's much larger. What will happen to the electron if it gets pushed in that direction? Well, now the electron, after the initial push, the electron will now be moving in that direction. So what will happen to the direction of the force? Well, again, keep using your left-hand rule, and then the magnetic force will be acting, I'll be acting in this direction now. There's my magnetic force be acting in that direction now. So this will cause the electron to then change direction again. So let's say the electron movement is now like that. Well, again, using your left-hand rule, at this point it's going to really feel kind of awkward orienting your hand properly, but that's okay. You get the idea is that the magnetic force is then going to be working in this direction. And this will continue indefinitely until the electron leaves the magnetic field. So like if the electron is still there, the electron is now being pushed in this direction, or moving in this direction. The force of the magnetic field will push it in that direction. And hopefully you guys can sort of see where I'm getting at. What kind of motion does this look like? There we go. So as you can see, the path of the electron, if this was a continuous path, I've not really drawn a really super continuous path, kind of looks like the electron is traveling in a circular path. And this is actually what will happen. If its magnetic field is large enough and the electron can stay inside it, the magnetic field will actually cause the electron to bend in a circular motion. As long as the magnetic field remains constant and the speed of the electron remains constant, it'll form a pretty perfect circular path. If any of that changes, it'll kind of create a spiral path. And this is kind of interesting because this is how particle accelerators will bend particle beams, is they will pass the charged particles through a magnetic field, and that magnetic field will cause the beam to bend. This is how we can get things like, which is kind of part of the reason why, if you remember our visit to Triumph, why the Triumph facility is kind of circular, because then the electrons can kind of bend in that circular path around the magnetic field that's created. Alright, so your assignment then for today will be as follows. If you guys have any questions, you know how to contact me.